What is error propagation in gas property calculations? Imagine you're trying to measure the size of a room, but your tape measure isn't perfect. Small errors in your measurements can add up, making your final estimate less accurate. The same idea applies when calculating gas properties in thermodynamics. When scientists or engineers measure variables like temperature, pressure, or volume, these measurements are never exact. Each one has a tiny amount of uncertainty, and when you use these measurements to find other properties, those uncertainties can spread and grow. This process is called error propagation. In calculations involving gases, we often use formulas that combine multiple measurements. For example, to find the volume of a gas using the ideal gas law, you need pressure, temperature, and the amount of gas. If your pressure measurement is slightly off and your temperature measurement also has a small error, the calculated volume will be affected by both errors. Error propagation helps us figure out how much these small measurement errors influence the final result. To understand how errors spread, we use mathematical tools that involve derivatives. These derivatives tell us how sensitive a property is to changes in each input variable. For example, if a small change in pressure causes a big change in the calculated volume, then the error in pressure will significantly impact the volume estimate. We also use variance calculations, which combine the uncertainties from all inputs to give an overall error estimate. This process is especially important when working with real gases, where simple models like the ideal gas law don't always fit perfectly. More complex equations of state are used, and these involve many variables. Each of these variables has some uncertainty, and error propagation helps us understand how these uncertainties affect the final calculated properties like enthalpy or entropy. In practice, the first step is to identify all the input variables and their uncertainties. Then, we apply the relevant thermodynamic formulas to relate these inputs to the property we are interested in. Next, we use error propagation formulas involving derivatives to estimate the combined uncertainty in the final value. This way, when engineers or scientists report their results, they can include a margin of error or confidence level, making their data more reliable. Knowing how errors propagate in gas property calculations helps us design safer and more efficient systems. It allows us to understand the limits of our measurements and calculations, ensuring that the results we use for decision-making are as accurate as possible. So, error propagation isn't just about math. It's about making sure our understanding of gases and thermodynamic systems is trustworthy and precise.